Now, we had defined this U. U of P is equal to U of P0 minus F dot dl from P0 up to P. This is what we call the electric potential energy of the system. This is an energy. So its unit is joule, so it has all the properties of energy that you know from mechanics courses. Now, if you remember, from the force, we had defined a related quantity, Q times E, the electric field. So we have this charge, small charge Q, and we had, it feels a force due to the electric properties, and that force is just the charge Q times the electric field at the point where the charge is. Or we can define, no, this is enough. So if you take the definition of the electric potential energy, so you have this system of charges which also contains one charge that we single out, this plus Q that we will call the test charge. So we have this test charge, and you calculate the potential energy and divide it by Q. This will be equal to U of P0 divided by Q minus, again from P0 up to P, E dot dl. Because F over Q is nothing but E. And of course we also take the limit as Q goes to 0. Now this is what we define as V of P0 minus P0 to P E dot dl. This is the electric potential. It's not an energy. Its units are not energy. If you can say that its units is joule per coulomb, or you can also say its unit is defined as volt. Unit of V is 1 volt. And in terms of volt, the electric field is usually defined in terms of volt. The unit of electric field is 1 volt per meter. This is the unit of the electric field. Now, the relation between the force and the electric field is the same thing as the relation between electric potential energy and electric potential. The only difference is, well, you don't have this energy here, just pay attention to that. They're completely different things. So electric potential is basically, electric potential at a given point is basically the electric potential energy the system would have if you would put 1 coulomb over there. So that's also another way of looking at this electric potential. Now we had already calculated the potential energy of 2-point charges. Questions? No, okay. So we had already calculated the electric potential energy for this configuration, and it was 1 over 4 pi epsilon 0 Q over Q, large Q over R. And then the electric potential, let's say this is created at the point P, is equal to 1 over 4 pi epsilon 0 Q over R. Now, electric potential energy was a property of the system as a whole, but electric potential energy is the properties of these charges over here. Also, there's a little subtlety that you have to pay attention to. For example, if you consider this system as a whole, what is the electric field at this point? At the position of the small charge Q, what is the electric field at that point? It is not Q, what over R squared? Epsilon 0, large Q. No, that is not the electric field at that point. That is the electric field created by large Q at that point. But there's also a charge at that point, the small q, which also creates an electric field. And the electric field at that point is in fact infinite. Now the thing that you have to pay attention to is whenever we are writing F is equal to Q times E, this electric field is the electric field created by the other charges, not this charge small q. So you don't include the contribution of this small q into this electric field over here. That's why we are taking the limit q goes to 0. So the electric field created by this charge also goes to 0. Now let's do a few examples about this electric potential energy and electric potential. Plus q, minus q, plus q, minus q. These, they are just placed at a rectangle. Now, what is the electric potential energy of this configuration? Of this configuration. I mean, you see, when we say we are looking, the electric potential energy is a property of the whole system. We are not, I mean, although we said that, okay, we are calculating the electric potential energy at this point, it's not really at a given point, at a given configuration. So when all the charges are placed like this, what is the electric potential energy of this system? Okay, one answer is 0. Sum of every pair's potential energy. Okay, the question will always be why 0 or why the sum of every pair's potential energy. So, now if we have one positive charge, one negative charge over there, the total charge will be 0, but our previous result. Now here we didn't, I mean, okay, in this result, we didn't assume anything about the positive charge, the small q and the large q. In principle, we can just take them to be opposite charges. The total charge will be 0. Nevertheless, I will have a potential energy. You can also think of potential energy as how much energy can you extract from the system. It's you have stored it over there, so you should be able to somehow extract it. So if you have one positive, one negative charges, somehow they will attract each other. So essentially you are extracting energy from the system. Well, that's what your friend said. Well, it will be basically your friend's answer. I mean, just pairwise addition. So you can always think of it, how much work do you need to do if you want to create this configuration from charges at infinity. So let's calculate the potential energy of this configuration. You can just bring the charges whichever way you like. I bring this positive charge Q first. So how much work I did? None. Then I brought this minus Q charge. How much work did I do? Well, let's take this 1 over 4 pi epsilon 0 out. How much work did I do to bring this minus Q charge to this point from infinity? Minus Q squared over A. Well, it's basically what we had calculated over here. 1 over 4 pi epsilon 0, the product of the charges divided by the final separation. This is the work that we had done in order to bring the system to this final configuration from charges at infinity. So I have this charge, and I have that charge. Now the next question, I bring this charge, my third step. How much work did I do to bring it up to here? Q squared over A root 2. Anything else? Minus you see, if as I bring this one to here from infinity, now I have these two charges already there placed. So I need to do work against the forces that are created by these two charges. Because this will be feeling a force due to both of these charges. Now I'm bringing the last one, this minus q. All these three charges are over there. I'm bringing this minus q charge. How much work do I need to do to bring this last minus q charge from infinity? This is due to the work that I have to do against this charge. There is also a work I have to do against this charge, which will again be minus q squared over a. And then there will be a work that I will have to do against this charge over here, which will be again q squared over a root 2. This is the potential energy of the system. And what will it become? 1 over 4 pi epsilon 0 q squared over a minus 4 plus 1 over root 2. This is the total work that I have to do if I want to bring the system to this configuration. And this will be the work that I can extract from the system. This is the energy stored in the system. This is the potential energy of the system. I have two such factors. Well, the same system, almost. I don't have this charge. That is my point P. What is the electric potential at the point P? Okay, V of P, let's start by 1 over 4 pi epsilon 0. It will be always there. What's the potential energy? Electric, not the energy, the potential. Already there. So this is the answer. So I mean, this is one of the main differences between the electric potential and potential energy of a given system. You see, this is not the potential energy. This is the potential. There, I don't put there anything. This is the electric potential of that point. So if I put a charge Q over there, it will have a potential energy equal to Q times this one. So I can extract that much energy from that single charge only. Not from the system, from that single charge. So this is the potential. And just like for potential energy, we can only calculate the differences. Also for the potential, we can calculate the differences. We can calculate the difference in the potential between 2 points. But there's nothing there. We are just looking at the potential of that point, in a sense. Now, this is the potential due to, let me just give the names to these charges. This is 1, this is 2, this is 3, this is 4. This is the potential due to the charges 1, 2, 3 at the point P. Here we have the potential energy of the configuration 1, 2, 3, 4, all of them. Now the next question, how can we really relate these things? Now the relation is not just simply U over Q is equal to V. I mean, that is one thing that I want you to see this. I mean, if I take this divide by Q, it doesn't give me this answer over here. It's not equal to this one. By the way, this is equal to 1 over 4 pi epsilon 0 Q over A minus 2 plus 1 over square root of 2. Let's say this is P4. This is the position of the fourth charge. This is the potential energy of the position of the fourth charge. What about the position of at the point of the first charge? Let's say this is P1. It will be the same. The potential of the point P1 due to the charges to, no, this is P2. 2, 3, 4 at the point, no, P1, 3, 4. At the point P2, this is equal to 1 over 4 pi epsilon 0 Q over A minus 2 plus 1 over root 2, right? Yes. No. In this one, yes, but I mean in general, no. Let us look at one more problem from the same system. Now this time I will be removing this charge. The potential energy due to second, third, and fourth charges at the point P1. Q over A. Okay. Now let's try to generalize this somehow. I have many charge distributions, Qi. The total potential energy of the system will be equal to, okay, I bring the first one. What is the work that I did? 0, no work done. Then I bring the second charge. The work that I have done will be 1 over 4 pi epsilon 0 Q1 times Q2 divided by R12. My first charge is already there. Now I bring the third charge. How much work do I need to do? Well, I'm bringing the third charge, so there is 1 over 4 pi epsilon 0, Q1 times Q3 times R13. This is the work that I need to do against the force due to charge 1. But then there is also 1 over 4 pi epsilon 0, Q2 times Q3 divided by R23. This is the force that I have to do against the charge 2, plus etc. Now, all of this I can just combine into 1 over 4 pi epsilon 0 Qi Qj divided by I Rj for j larger than I. J is the last charge I bring, and I'm summing over all of them. I will be eventually bringing all the charges, and I have to do work against the charges that are already there, against the Qi's. So I need to sum over for each j, I have to sum over the i's. So if you just look at here, when j is equal to 2, I can only take the value 1, so I have a single term. When j is equal to 3, I can be 1 or 2, etc. Shall we write one more line over here when we bring the fourth charge? Now, when we bring the fourth charge, well, we are doing work against Q1. This is the work that we do against Q1, plus 1 over 4 pi epsilon 0. We are doing work against Q2, plus 1 over 4 pi epsilon 0. We are doing work against Q3, plus the rest, which is basically this expression over here. Well, I can write the same thing like this also. This is equal to sum over I different than j, 1 over 4 pi epsilon 0, Qi Qj divided by I Rj divided by 2. Now, why? Because when I remove the condition that j is larger than I, okay, I have a term like 1, 2. I also have a term 2, 1. Well, if you look at here, I only have 1, 2 once, not twice. Here I have a single term Q3, Q2. Here I have Q3, Q2, and also Q2, Q3 in the sum. But here I have a single term, not 2. Now, in this sum, all these terms are double counted. So I divide by 2. Now, what is the advantage of this sum? This is equal to 1 over 2. Well, I will sum over j. First, I sum over the I. Qi over Ij times 1 over 4 pi epsilon 0. Now, let me write it like this. Now let's look at this sum. What is this sum? It's the electric potential. It is the potential created at the point Qj times the potential energy created at the point Qj by all the other charges than Qj. Not the same charges, but other charges. And so you calculate the potential created at the point of each charge, multiply it with the potential created by other charges, multiply it by the charge at the point Qj. That is the potential energy of that Qj. And that is the work that you have done in order to bring Qj only there. Sum it over all j, divide by 2 to avoid this double counting, and this is the total work, the total potential energy of the system. Not of that single charge, but of the system. This is the potential energy of the system. In other words, that is the work that you have to do to bring all the charges to their final configuration, starting from charges at infinity. Questions? Yes. Well, I mean, it doesn't make any difference how you come to the final configuration. You will always get the same energy, same total energy. You see, here we have some different concepts. We have the electrostatic energy of the system as a whole, electrostatic energy stored due to the, you bring a single charge to a given point, assuming all the other charges are fixed relative to each other. And then you have the electric potential at a given point. Now, when you calculate the electric potential at a given point, put a charge over there, you are obtaining a potential energy, but that is the potential energy for creating this final configuration, given that all the charges except and the last one you put are already there. So it is that potential energy. So in your words, you are just moving the rest of the charges as a whole. The potential energy of the system, without really specifying anything else, will be just how much energy you did to bring your charge configuration into the final state. Questions? Well, there's one question I have then. What about the electron? We said we are always talking about the single charges, point charges. How much work did we do to bring that single point charge into existence? No. If you try to calculate it, it just turns out to be infinite. How much energy? I mean, we said that the potential energy of a given system, electric potential energy of a given system, is the amount of energy stored in the system, or the amount of work that you had to do in order to bring all those charges into their finite configurations, starting from charges at infinity. But we are always talking about point charges. Do they have a potential energy? What is the potential energy of a point charge itself? How much work did you have to do in order to bring that configuration into existence? It turns out to be infinite. But that infinity just turns out to be also irrelevant. Because electrons, you cannot divide electrons. Electrons always stay there. Although its potential energy, self-potential energy, turns out to be infinite, since we are only dealing with potential energy differences, they always turn out to be finite, because you cannot destroy electron. No, I can. Why shouldn't I? This is just a side note. I mean, if it doesn't make any sense to you for the time being, forget about it until you study some particle physics. Now, let's do one more thing before we go for a break. Okay, we started with the electric field. We know that we started from the forces that describes everything about the electrostatic interactions of particles. Then we said, okay, let's forget about the forces. Let's concentrate on the electric fields. We can express the electric field in terms of, we can express the force in terms of the electric field. That was one step. And now from the electric field, we are calculating the electric potential. We calculated the electric potential energy, and we calculated the electric potential. So given the electric field, we can calculate the electric potential by just evaluating this integral over here, E dot dl. We just evaluate this E dot dl integral, just like we we evaluated f dot dl integrals, so we have the electric potential. But eventually we would like to know the forces. So that will tell us how our system will behave, our system, what will be the dynamics. So the forces will be related to the electric field. Given the electric field, we can determine the forces. Now if you go to switch to the potential, from the potential, how can we obtain the electric field? I mean, if we cannot obtain the electric field from the potential, then what's the point in studying the potential? If it doesn't contain all the necessary information. So let's see how we can calculate the electric field from potential. Now, let us first write down the definition of the potential difference between 2 points. From P0 up to P. Now, this is valid for any 2 points. Let us just imagine we take 2 very small nearby points. 2 points that are separated by a very small distance. This is P0, this is P. This is my dl. Well, I don't need to divide my integral, my line, this line connecting P0 to P into even smaller intervals, because it's already small. And we will eventually assume that its length goes to 0, so point P0 and point P will be at the same point. So along this line, electric field, we can just assume that it is constant. So there's a constant electric field between P0 and P. So the change in the potential energy, electric potential, sorry, let's call it Vp minus Vp0. Delta V is nothing but E dot, let's say, delta L. I'm just meaning the same thing. I will just be using different symbols. They are the same, just different symbols. This will be true for all delta L sufficiently small. That's true for any point. Now I can assume delta L, I mean this is valid for any delta L. I can just look at this relation for, let's say, delta L is equal to some length times in the x direction. In this case, E dot delta L is nothing but the component of the electric field in the x direction times, well, instead of delta L, let me use delta x times delta x. This is my E dot delta L. So the electric field, the component of the electric field in the x direction is, no, here I have a minus sign, by the way, is nothing but minus delta V by delta x. This is the electric field in the x direction. No, I have a minus sign over here. This minus sign is this minus sign. Now, what is this delta V? We said that it is the minus the potential at the point P. Let me just denote the position of the point P as x, y, and z, minus the potential at the point x0, P0. Well, P0 and P, they only differ by their x components. The point P0 has an x component that is less by x0, y, and z, divided by, well, delta x. Now let me sorry. This is x0 divided by x minus x0. This is what I call delta x. Delta x is the difference of the x. This just tells me that point P and P0, they only differ along, I mean, if you take point P0, shift it along the x-axis by delta x, then you reach the point P. This is what this choice means. So x0, and this is the potential at the point x0. This is the potential at the point x divided by x minus x0. Well, this is true as long as delta x is sufficiently small. Well, infinitesimal is sufficiently small. So I will take limit as x goes to x0. Well, that limit is nothing but the derivative. So electric field, the x component of the electric field at the point x, y, z is nothing but minus the derivative of the electric potential at the point x, y, z. This is the electric field, the x component of the electric field. Well, you can just repeat the same derivation for the y and the z components. You will just assume, you only need to assume that this delta L, instead of in the x direction, you can just take a delta L to be in the y direction. You take a third delta L in the z direction. And in each one of these cases, you will have electric fields in the y direction, and then you will have the electric field in the z direction is nothing but the derivative of the potential with respect to the z. So the potential, electric potential carries, well, this basically means that electric potential carries the same information as the electric field. So you can just obtain the electric field from the definition of the electric potential. So rather than working with the electric field, you can work with the potential, and still you will be able to obtain the same results because they carry the same information about our system. Any questions? Let us just make one more definition. Well, the electric field is the x component in the x direction, the y component in the y direction, plus the z component in the z direction, which we can also write as in the x direction minus the derivative of the potential with respect to x, or I will just take the minus out. In the x direction, derivative with respect to x of the potential. In the y direction, the derivative of the potential in the y direction with respect to y. In the z direction, the derivative of the potential with respect to the z. This is just a statement of the previous results. The x component of the electric field is minus the derivative of the potential with respect to x. The y component is minus the derivative with respect to y. The z component is minus the derivative of the potential with respect to z. Just for notational simplicity, rather than writing such long expressions, you will see in your future years more often that this we write as, this is just a definition. It is minus del y del x plus y hat v. Again, this is just a notation. This last line just means this, and which is also defined as minus. This is again just a definition. This symbol over here, inverted triangle, is just a shorthand rotation for everything written in the square brackets. Just symbol. And this is called the gradient. Now, some of you were asking what the gradient was. This is how we define the gradient. Again, it is just a symbol to show all this line. Since this combination always comes, you will see this combination quite frequently all the time. So rather than writing all these long expressions, we just write this symbol. Well, this is what we call a differential operator. If you want to call it an equation, you have to write an equation. Okay, let's go back to our potential and let's try to calculate something. Now, we had already calculated the potential of a point charge, and we said that this was equal to 1 over 4 pi epsilon 0 times Q over R. Or let's write it in terms of x, y, and z components. This is 1 over 4 pi epsilon 0 Q times x squared plus y squared plus z squared to the power minus 1/2. Now that is nothing but a fancy way of writing 1 over R. Let's calculate the electric field in the x direction. Well, we know that the electric field in the x direction is minus dV by dx. V is given in the first line. This is equal to minus 1 over 4 pi epsilon 0 Q. Now the derivative of that whole thing with respect to x, we just use the chain rule. So it's just a polynomial. The derivative of the polynomial would be, well, not a polynomial, but just a power, minus 1 over 2 times x squared plus y squared plus z squared raised to the power minus 1/2 minus 1. I just reduced the power by 1. Then I need to take the derivative of what is inside with respect to x, but that is 2x. Now this minus will cancel this minus. This 1 over 2 will be cancelled by this 2. So the electric field in the x direction is nothing but 1 over 4 pi epsilon 0 Q times x over R cubed. Why R cubed? Well, here I had minus 1/2, minus 1 is minus 3/2. The square root of this thing is R. So I take the 3/2 power is just R cubed. It's not R squared. Now you do the same thing for EY. If you do the same thing for EY, you need to take the derivative with respect to the y. It will be the same thing over here, but instead of taking the derivative of this whole thing with respect to x, you need to take the derivative of this whole thing with respect to y. And that would bring a 2y over here instead of 2x. So here I would just have y instead of x. And then finally Ez, Q times Z over R cubed. These are the components of the electric field obtained from the electric potential. Let us write the electric field vector. Well, all of the components have this factor. They all have Q over R cubed. The x component has x, the y component has y, the z component has z. And this vector is nothing but the R vector. So this is equal to 1 over 4 pi epsilon 0 Q over R cubed in the R direction. This is 1 over 4 pi epsilon 0 Q over R squared in the R hat direction. This is the famous cube that we had discussed also when we were talking about the Coulomb's law. this cube. It is still an inverse squared law. Because the magnitude, the amplitude of this one is 1 over r squared. This has the length r. Any questions before you go for a break? Okay, a 15-minute break.